Hi, this is Sai Putana, founder at Embedded Systems AI LLC. Welcome back to the Distributed Design Pattern Catalog. In the last installment, we covered how services communicate. Now we turn to a harder question, arguably the hardest question in the distributed systems. How do you store data across multiple machines and keep it correct? The core principles at the top tell you what's at stake: consistency, availability, partition tolerance. That's the CAP triangle. But also durability, recoverability, scalability, and isolation. Every pattern in data management and consistency patterns makes a deliberate trade-off among these seven forces. There's no free lunch in distributed data. You're always trading something. Let's start with the replication patterns. Three different answers to the question, where do writes go? In section 1, leader-follower replication is shown. One node is the leader. It accepts all writes. Followers replicate the leader's state asynchronously or synchronously and serve read traffic. This is what PostgreSQL streaming replication, MySQL primary replica, and MongoDB replica sets all use. The mental model is simple. Consistency is straightforward because there is exactly one source of truth for all writes, and failover is well understood. Promote a follower. The downsides are equally well understood. The leader is a write bottleneck, and during failover, you risk split brain if two nodes both think they are the leader. This pattern can be used when write volume fits in one node and you want simple semantics. In section 2, multi-leader replication is shown. Multiple nodes accept writes, and changes replicate between leaders. This is what you do when you have multiple data centers. You want local writes in each region. Examples are Cassandra in multi-DC mode, CouchDB, and React. The huge benefit is low write latency everywhere and no single write bottleneck. The huge cost is conflict resolution. If two leaders accept conflicting writes to the same key at the same time, you have to merge them somehow. Last write wins, vector clocks, application-defined mergers. Every option has sharp edges. In section 3, leaderless replication is shown. It's often called Dynamo style after Amazon's original paper. There is no designated leader at all. Writes can go to any node, which act as a coordinator, and data is replicated via consistent hashing and versioning. DynamoDB, Cassandra, React are examples of this pattern. This pattern is the high availability champion. No single point of failure. Linearly scalable. Tolerates node failures gracefully. The cost is eventual consistency by default. And you need mechanisms like read repair and quorum reads to get stronger guarantees when you need them. In section 4, the quorum pattern is shown. This is the knob that makes Dynamo-style systems usable. Operations only succeed when a required number of nodes respond. R nodes for reads, W nodes for writes, out of N replicas. The magic formula is reads plus writes greater than number of nodes, which guarantees that any read overlaps with at least one node that has the latest write. You can tune this per operation. R equals 1, W equals N for fast reads and strong writes. R equals N, W equals 1 for the opposite. R equals quorum, W equals quorum for the balanced middle. Misconfiguration here is one of the most common ways production systems lose data. In section 5, eventual consistency is shown. All replicas will converge to the same state given enough time and no new writes. No guarantees on when. DNS, CDN caches, S3 metadata, Cassandra defaults to this. The diagram depicts this nicely. At time 0, node A has x equals 1, while nodes B and C have x equals 0. By T3, all three have x equals 2. In between, reads can return stale data. This is the price you pay for high availability and partition tolerance. And for many use cases, like social feeds, product catalogs, analytics, it's the right trade-off. For other transactions like bank balances, inventory counts on the last item, this pattern is a disaster. Now we move on to consistency models. In section 6, strong or linearizable consistency pattern is shown. All operations appear to take effect atomically at a single point in time, in a global order that all clients agree on. This is the gold standard, the most predictable model, the simplest application logic, no stale reads. Systems like etcd, Zookeeper, CockroachDB, and Spanner all aim for this. The cost is significant. Lower availability under partitions per cap, higher latency because you need consensus on every write, and harder global scaling. This pattern is used when correctness is non-negotiable. Some example scenarios would be configuration data, leader election, and financial ledgers. In section 7, consistency models beyond strong is shown. Strong consistency is one point on a spectrum, not the only option. Read your writes guarantees you always see your writes, important for user-facing systems where a user posts a comment and expects to see it. Monotonic read says reads never go backwards in time. Once you have seen version 5, you won't subsequently see version 3. Monotonic write orders a single client's writes. Causal consistency preserves cause and effect. If write B depends on write A, everyone sees A before B. And eventual consistency, the weakest, just promises convergence. In section 8, the SAGE pattern is shown. The answer is, how do I do a transaction that spans multiple services when I can't use a database transaction? You break the transaction into a sequence of local transactions, each with a compensating action that undoes it. There are two flavors: orchestration, where a central coordinator drives the sequence, And the second one is choreography, where services react to each other's events without a central brain. Orchestration is easier to reason about and debug. Choreography is more loosely coupled but harder to trace. Either way, you get no global logs, you handle failures gracefully, but you lose acid. And writing correct compensating actions is genuinely hard. How do you uncharge a credit card? You issue a refund, but the refund itself might fail. In section 9, two-phase commit and three-phase commit is shown. 2PC is the classic distributed transaction protocol. A coordinator asks all the participants, "Can you commit?" And if everyone says yes, it tells them commit. Strong consistency. Asset semantics. Well understood. The fatal flaw is in the name. It blocks. If the coordinator crashes between phases, participants are stuck holding locks indefinitely. 3PC adds a third phase to reduce blocking, but it doesn't fully solve it and is rarely used in practice. You see 2PC in distributed databases, XA transactions, and financial systems where consistency requirement is absolute and the availability cost is acceptable. Most modern systems avoid it in favor of sagas. In section 10, the outbox pattern is shown. One of the most underappreciated patterns in this whole catalog. The problem it solves is the dual write problem. When your service needs to update its database and publish a message to Kafka, you have two systems and no transactions across them. If the database commit succeeds but Kafka publish fails, your event is lost. The outbox solution is elegant. Write the outgoing message to an outbox table in the same database transaction as your business data. A background process then reads the outbox table and publishes to the message broker. Now you have atomicity. Both the business write and the event are committed together, or neither is. The cost is extra storage and a background process to run, and events are published with a small delay. But you have eliminated an entire class of data loss bugs. Down at the bottom, the How to Choose guide distills the decision. If there's a need for strict correctness, strong or linearizable plus 2PC is preferred. If you need high availability and scale, eventual consistency plus quorum or dynamo style is preferred. If you need geo-distributed writes, multi-leader or dynamo style is preferred. If you need distributed transactions across services, Saga is preferred. For reliable event publication, Outbox is preferred. Part 1 covered replication, consistency models, and transactions, the load-bearing concepts. Part 2 is about the patterns that build on top of them, how the data flows between the systems, how reads and writes are optimized separately, how replicas heal themselves, and how data is partitioned to scale. Section 11 is the Change Data Capture Pattern, or CDC. This pattern captures changes from a database, inserts, updates, deletes, and streams them to downstream systems in real time. The trick is that CDC doesn't fold the database with queries. It reads the database's own transaction log. This is non-invasive. The source database doesn't even know CDC is happening. and it gives you near real-time updates with multiple consumers supported. The complications. Schema evolution is tricky because old events have old schemas, ordering guarantees depend on your transport, and you typically get at least once semantics, which means downstream consumers must be idempotent. This pattern can be used for replication, analytics pipeline, search indexing, and cache invalidation. Section 12 is the materialized view pattern. Pre-compute and store the results of an expensive query. Refresh it on a schedule or incrementally, and serve reads from pre-computed view instead of rerunning the query every time. Reporting dashboards, search indexes, and aggregations all benefit. The performance win is enormous, milliseconds instead of seconds, and you offload complex queries from your transactional database. The trade-off is that the view is always slightly stale. Refresh overhead is real, and incremental refresh logic gets complex fast when the source data has updates and deletes and not just inserts. Section 13 is CQRS pattern. Command Query Responsibility Segregation. In this pattern, reads and writes have fundamentally different requirements. So stop forcing them through the same model. Use the right model optimized for business rules and consistency on the command side. Use one or more read models optimized for query patterns on the query side. Events flow from the command side to the read side. The benefits are real. You can scale reads and writes independently, optimize each for its workload, and support multiple read models for different UIs. The costs are also real. More code, eventual consistency between two sides, and duplicated data. CQRS is the right answer for high-scale systems with complex query needs and overkill for simple CRUD. Section 14 is the event sourcing pattern. Don't store current state. Store the sequence of immutable events that produce the current state. If you want to know the balance, replay every deposit and withdrawal. If you want to know the balance as of last Tuesday, replay up to last Tuesday. The audit trail is free because it's the source of truth. You can derive new read models retroactively by replaying history with new logic. Time travel debugging becomes possible. The costs. Replaying millions of events on every load is impractical, so you need snapshots. Schema evolution of old events is genuinely painful, and the storage footprint is larger because you keep history forever. This pattern is used for financial systems, audit-heavy domains, and anywhere the journey matters as much as the destination. Section 15 is hinted handoff pattern. This is a small but elegant pattern from the Dynamo playbook. When a node that should receive a write is temporarily down, another node accepts the write on its behalf and stores it as a hint. When the down node recovers, the hint is delivered. The benefit is that temporary outages don't cause write failures or data loss. The system aborts them transparently. The cost is potential duplicates if the hint and the recovered node's own state diverge. Extra storage for hints and cleanup complexity. You see this in Cassandra, Dynamo-style systems, and mobile or edge sync scenarios where nodes are frequently offline. Section 16 is read repair pattern. When a client reads from multiple replicas and detects that one of them has stale data, the system automatically corrects the stale replica during or after the read. This is one of the mechanisms that makes eventual consistency converge in practice. Every read is an opportunity to detect and fix divergence. The benefits are self-healing replicas and improved eventual consistency without a separate repair process. The downsides are extra read overhead, the fact that read repair only fixes data that is actually being read. Cold data stays divergent, and the risk that it can mask deeper replication problems by quietly fixing them. Section 17 is the anti-entropy with Merkle trees pattern. This is the heavy-duty cousin of read repair, designed to synchronize entire datasets between replicas efficiently. Each node builds a Merkle tree, a hash tree, over its data. To compare with another node, the two exchange tree digest level by level. Matching hashes mean matching subtrees. Only the differing subtrees need detailed comparison. This lets you reconcile huge datasets while transferring almost no data when replicas are already in sync. The cost is CPU overhead to maintain the trees and complexity to implement correctly, but the bandwidth savings are dramatic. Section 18 is the partitioning strategy. 4 common approaches. Hash partitioning distributes keys evenly via hash function, great for load balance, terrible for range queries. Range partitioning splits by key ranges, great for range queries, prone to hotspots if your access pattern is queued. List partitioning splits by explicit value lists, useful for geographic and tenant-based partitioning. Directory-based partitioning uses a lookup service to map keys to partitions. Most flexible, but lookup service becomes critical infrastructure. The choice depends entirely on your access patterns. Section 19 is the vertical versus horizontal partitioning. Vertical partitioning splits a table by columns, hot columns in one place, cold columns in another. Useful when a row has many columns, but most queries need only a few. Horizontal partitioning, which is what most people mean by sharding, splits a table by rows, with each shard holding a subset of the rows. Shard 1 has user IDs 1 through 10,000. Shard 2 has user IDs 10,001 to 20,000, etc. Horizontal scales to massive datasets, but makes joins across shards expensive. In practice, large systems use both vertical and horizontal partitioning. Section 20 is about database per service pattern. One of the foundational microservice patterns. Each service owns its own database. No shared schemas. No cross-service queries at database level. No other service can touch your tables. The benefit is true autonomy. Services can evolve their schema independently, choose the database technology that fits their workload, and scale storage independently. The costs are equally real. Cross-service queries become complex, often requiring API calls or event-driven aggregation. Data duplication across services is the norm, and distributed transactions are off the table, which is why patterns like Saga and Outbox exist in the first place. This pattern is the deepest reason why microservices are hard. It pushes a lot of complexity from databases into the application layer. One thing worth saying out loud, the patterns discussed in this video are some of the deepest engineering ideas you'll ever encounter. Replication, consensus, partitioning, event sourcing, these are the problems people have been working on since the 1970s, and we still don't have a universal correct answer. We have a toolkit. Picking the right tool for your specific consistency, availability, and scale requirement is the engineering judgment that separates senior distributed systems engineers from everyone else. Thank you.